Right, travel graphs. As I say, something we first looked at a long time ago. Of course, travel graphs in year 7 or year 8, always nice and easy, lovely straight lines, you remember, and you go, oh, look, what's that? Now we can use curves. A ball is bounced, as you do, and its distance from the ground is graphed. And so there it is. So there is a travel graph, but unlike those ones that we saw all those years ago, it's not a straight line. It's a parabola, you will notice. The equation of that particular one is 5t8 minus t. Now, some terminology. Distance, obviously we know that, the total amount travelled. Whereas displacement is how far are we from the starting point or some reference point. I could walk 50 metres in that direction and then come back here, and even though I've travelled a distance of 100 metres, my displacement is 0 because I haven't got anywhere. I'm still where I started from. Okay. Find the height of the ball after 1 second. Well, we could read off the graph, or we could just substitute into the nice little formula that they've given us, and we end up with 35. Okay, nothing too mind-blowing here at the moment. At what other time is the ball the same height above the ground? Okay, so when else is it 35? And we end up with this quadratic to solve. Of course, it's very easy to solve because we already know one solution, and that was t equals 1. So therefore, it must factorise to be t minus 1, t minus 7. So after 7 seconds is the other time. All right, another term, average velocity. Okay. We know speed equals distance over time. Okay. Velocity is displacement over time. But if we're talking average velocity, then it's the change in the displacement over the change in time. So if we think of it like the slope of graph, if you like, x2 minus x1 over t2 minus t1. Now, it's not a coincidence that turns out to be the slope formula, because we're talking about rates of change. How does displacement change with respect to time? That is velocity. So the slope of the graph, of course, it gives us velocity. So find the average velocity during the first second. So use our slope formula, or x2 minus x1 over t2 minus t1, 35. So during the first second, it was 35 metres per second. During the 5th second, so the 5th second would start when t equals 4 and go to when t equals 5. So t equals 4, we need to find out where it is. It was at 80. And t equals 5, it's at 75. So again, we can use our formula. Negative 5. This is another difference between velocity and speed. You can have negative velocities. Now, negative in this terminology doesn't mean slowing down at a rate of 5 metres per second. Negative and positive talks about directions. So once I define the direction to be positive, negative just means I'm travelling in the other direction. So on average, it's negative 5 metres per second. Well, the whole 8 seconds, it's in the air. Something amazing happens with this average velocity. We're going to throw something in the air, it's going to come back to Earth, and the average velocity is 0. Ooh, the average velocity is it didn't move at all. That makes sense. It's back to where it started from. There was no change in the displacement. So that's, again, the difference between speed and velocity. So speed, as I say, that classical formula that we've seen for a very long time now, speed, distance over time. So the average speed, well, that's a different question. That's not going to be 0 because it certainly has travelled a distance. And it travelled 160 because it went up 80, down 80, and that was in 8 seconds. So we get 20 metres per second was its average speed. All right, that's all I'm going to talk about for the travel graphs at this stage. We'll certainly look at them in a bit more detail later.